3.3, graphing rational functions of the form f of x equals ax plus b over cx plus d. Today's learning goal. Okay, by the end of today's lesson, you should be able to graph rational functions that have linear expressions in both the numerator and the denominator. And you should be able to determine key features of these rational functions. Now, you already know how to graph this type of function, b over cx plus d. That's an example of a reciprocal linear function, and we've been working on that. But you haven't learned how to graph something like this, where you've got a linear expression in the top as well as the bottom. So that's going to be our generic form, ax plus b over cx plus d. I'm just going to go through some of these characteristics, and then we'll do some examples, and we'll go back to this if we need to. So these graphs usually have a vertical and a horizontal asymptote. There sometimes is an exception. We'll talk about the exception in a second. So for vertical asymptotes, we know that that arises because we've got division by 0 in the bottom, in the denominator here. So that would mean that if this whole thing is 0, then x would have to be equal to negative d over c for that to occur. Okay? So if we had it in this form, we could just find negative d over c, and we would have the equation of the vertical asymptote. Now, I've already told you many times that the equation of the horizontal asymptotes for a reciprocal linear function, and indeed a reciprocal quadratic function, are y equals 0 or f of x equals 0. For a linear rational, where you have a linear in the top and the bottom, you would have a horizontal asymptote at y equals a over c, where a and c are the coefficients of the x. And there is an exception to that, and the exception would be that if you had a common linear factor that you canceled out in the numerator and the denominator, and you result in a linear graph, then you're going to end up with a hole where the common factor was that you canceled, and your graph will contain no asymptotes. So I will explain that more in detail when we get to an example like that. Okay, the graph of ax plus b over cx plus d has an x-intercept where y equals 0, of course. And algebraically, this is going to equal minus b over a. Why? Because the y can only become 0 if 0 is in the numerator. Because if 0 is in the denominator, that's a vertical asymptote. So 0 in the numerator would be if you had ax plus b equal to 0, so x would have to be negative b over a. And of course, you remember that the graph of a reciprocal linear does not have any x-intercepts because we had a horizontal asymptote at y equals 0 at the x-axis. Okay. The y-intercepts, you're just going to figure those out because you're going to substitute x equals 0 into the equation. So 0 here, meaning it's just going to be b over d. And if it's 0 here, same thing, b over d. Okay, all right. So this is ax plus b over cx plus d. Oh, let's just clear that, sorry. Okay, clearing from page. So it says, determine the horizontal and vertical asymptotes of f of x equals ax minus 1 over minus x minus 5. Linear in the top, linear in the bottom. This is no longer a reciprocal linear function. That would have only had a number, a constant in the top, and so usually 1. So we know that we're going to have to use some of our rules. So let's just write this down again. If f of x is equal to ax plus b over cx plus d, then we've got the horizontal asymptotes, so I'll call that horizontal asymptotes, are, as you recall, the coefficients of the x terms. So the horizontal asymptotes take the form y equals, or you could say f of x equals, it's going to be 8 over negative 1. So f of x equals negative 8. So we've got a horizontal asymptote way down at negative 8. The vertical asymptote, so I should have maybe, for your benefit, written f of x equals a over c. So that's the formula. I try not to remember the formulas too much, but for the horizontal asymptotes, you kind of have to take my word for that one. The vertical asymptotes, well, they're going to take the form x equals, and again, if you want to use the formula, I think it was for the vertical asymptotes, it was minus d over c. So x is equal to, if this is d, because it's plus here, so we're not taking the opposite sign anymore. So if this is d, then minus d would be 5, and if this is c, then we're just going to put negative 1 here. So the vertical asymptote is x equals negative 5. But you already knew that, because if you put in negative 5 here for x, a negative of negative 5 is positive 5, and 5 minus 5 is 0. So another way to do this, if you forget about the letters, if you just set the bottom equal to 0, if you just say minus 5 is equal to 0, and then you rearrange and solve for x, that is your vertical asymptote. Okay, so a couple of different ways to do it. So we figured out what the vertical and horizontal asymptotes are. Let's do example 2. It says determine the x and the y intercepts of this function. And again, linear over linear. Be careful. If you want to put it in the form ax plus b over cx plus d, then you need to rearrange this. So it's 7x plus 4. So if I want the y-intercept occurs where x equals 0, of course, and the y-intercept then is just going to be this 5 over 4, right? Because when we put 0 in here and here, it's just 0. So we're going to have f of 0 equals 6 times 0 plus 5. I'll just do it. 7 times 0 plus 4, which is equal to 0 plus 5, and 0 plus 4, which is equal to 5 over 4. Or, so that's one way to think of it, or you know that, so f of 0, you could call this y equals, that your y-intercept is just b over d. So y equals 5 over 4. The x-intercept occurs where y equals 0. This one's trickier. So this is your y, so this is 0. So you could algebraically just do 0 equals 6x plus 5 over 7x plus 4. And then if you think about it, really it's like cross-multiplying. And if you're cross-multiplying, that would be 6x plus 5 equals this times this, and anything times 0 is 0, so just put 0 there, and we end up with 6x equals negative 5, and x equals negative 5 over 6. Or the other way you could think about it, using the letters, would be that x equals the minus b over a. So x is equal to minus 5, because this is b, so this is minus 5 over my a, which is 6. Okay. It says determine the positive and negative intervals of this rational function. So the intervals consist of the vertical asymptotes and the x-intercepts. So we must determine both. Okay. So I need to maybe just pull up the graph of that first, because we haven't graphed any of these yet, have we? So why don't we go to Desmos? I'm just going to do that right now. I'm just going to call up. Let's see if this will work now. Desmos.com. And we're going to put in the equation minus 4x plus 5 over x plus 8. I'll put it in brackets. Divided by, what was it? X plus 8? Yikes. I think I'm going to have to go back and check. Yeah, okay. And then I'm going to just maybe zoom out, and we can see that we have this lovely graph. Okay, now visualize a nice vertical asymptote here. Can't quite figure out what the value of it is by looking at it, but that's okay. It looks like there's also a horizontal asymptote here, not at y equals 0. And so if we're being asked to find the positive and negative intervals, this is trickier than when you have a horizontal asymptote at y equals 0, because you're going to think, all right, it definitely changes at the vertical asymptotes, right? This has gone from now at the vertical asymptote being negative to being positive, so we've got to consider the vertical asymptotes for sure, but also we consider the zeros, right? Because in this branch here, it's gone from being positive, and then it hits a 0 here at the x-axis, and now it's negative. So two places potentially where changes can occur. So we are going to go back here, and we're going to find the vertical asymptotes and the x-intercepts any way you want, algebraically or using your A's and B's and C's and whatever. Just come up with them. So vertical asymptotes, I know that's x equals negative 8, right? It's where you have division by 0 in the bottom. Okay, and then the x-intercept occurred for y was equal to 0. So if you have 0 here, then you're just going to set the top equal to 0. That's the only way that you're going to get this side equal to 0 is if the top of this is equal to 0. So you're going to say 0 equals minus 4x plus 5. Negative 5 equals minus 4x, and x is equal to 5 over 4. Okay, so now we have to test using intervals created with both the vertical asymptote and the x-intercept. So we're going to go starting back here, oopsie, wrong one, at negative infinity all the way to either our first 0 or our vertical asymptote. So we're going to hit a vertical asymptote first, then we're going to hit a 0, and then we're going to keep going onward to infinity. All right, so we've got the first interval then is going to be negative infinity to our vertical asymptote, negative 8. So whatever the lower value is, it's just like before, that's what we're starting with. And then we're going to go from negative 8 to our 0. And then we're going to go from our 0 to infinity. And we're going to test, and it's going to look a little different now, because what we're doing is we're testing the top and the bottom. Instead of with the polynomial functions, you know how we were just always multiplying together? Well, this is the top, this is the bottom. We want to know if the whole thing is positive or negative. So we can have another little thing here saying result, and then we'll just decide whether it's positive or negative. Okay, let's start here. I'm just thinking. Negative infinity to negative 8, so if we put in negative 100 would be positive here, so this is going to be positive. Negative 100 here is going to be negative. And when I divide a positive by a negative, I get a negative. So that means that the result of this is negative. I guess I don't really need this. So we know that this interval is negative. Between -8 and 5/4, how about 0? If we put in 0 here, sorry, I should go over here. That's 5, that's positive. Put 0 in here, that's positive. And that positive divided by a positive is a positive. Put in positive 100 here. Positive 100 would be -400 plus 5, which is negative. And positive 100 here, it would be positive. And these divided would be a negative. Okay, let's just go back and see if that makes sense. Was our graph negative between -infinity and -8? And then did it become positive until we got to the other 0? And then did it become negative afterward? I'm going to say, I do believe. Negative till we got to the horizontal or the vertical asymptote, and then it became positive until we got to that 0, and that's not a 0, that's at 5/4. And then from 5/4 onward, it became negative. So all of those are round brackets. We cannot be at -8, and we cannot touch the 0 for positive or negative intervals, right? Because if we're on the 0, then we're on Switzerland. Remember, it's neither positive nor negative. So determine the positive and negative intervals. So I'm going to say it is positive when x is an element of -8 to 5/4, round brackets, and it's negative when x is an element of -infinity to -8, and from 5/4 to infinity. There we go. All right, tricky. Let's keep on going. Determine the domain, the intercepts, the asymptotes, and the positive and negative intervals of f of x, and then sketch its graph. All right. I have enough room here. Okay. Well, the domain. We can do that in a minute. Let's start with the intercepts. So x-intercept, y equals 0. And so we're going to have 3x minus 1 equals to 0, 3x equals 1, and x is 1/3. So there's an x-intercept, y-intercept, x equals 0, that's easy, so the y-intercept would be 1/2. And we put in 0 and 0 here, and we end up with 1/2. So x-intercept, y-intercept, asymptotes, so we'll just do the horizontal asymptote. Remember, horizontal asymptote is the coefficients of the x's, so that's going to be a over c. No, sorry. I don't like writing horizontal asymptote equals. So it should be, because that's horizontal asymptote is y equals, we would use f of x equals a over c. So f of x is equal to 3 over 1, which is just 3. Vertical asymptotes occur where x, in this case, is equal to 2. Right? Okay. Positive and negative intervals. I'm going to create those positive and negative intervals down here, and then we'll talk about the domain. Well, we can talk about the domain now. You can see that the domain is everything but the, if you go back to kind of looking at what we saw over here, to give you a little clue, these graphs are going to be very similar. You're going to have a domain that is just everything but the vertical asymptote. So your domain in interval notation would be -infinity to 2 round bracket because we don't want to touch that vertical asymptote and then jump it on over and get it going to infinity. So if we're going to break this into our intervals, remember we only use the vertical asymptote, or totes if there were more than one, but with linear ones there's just one, and then the x-intercept as well, so over here. So that's what we're using always. That's going to create our positive and negative intervals. Okay, so we start with the smallest number, so that's going to be negative infinity to a third, and then a third to 2, and then 2 to infinity. Okay, we're also going to break it then into its top, 3x minus 1, its bottom, and the whole thing, which is, I can write it out, or you can just call it f of x. Okay, so we test. Minus 100, that's negative. Minus 100 here, that's negative, and when we divide those, it's positive. Something between a third and 2, try 1, that's positive, and that's negative. So our result will be negative. And 2 to infinity is like 100 in here is going to give us a positive value. 100 in here gives us a positive value, and this is going to be positive. So we know that we have positive intervals between negative infinity and 1/3 and between 2 and infinity. Okay, that's going to help us graph this. So let's see if we can just put everything that we've learned on our graph. I'm going to try and make it as neat as possible. So let's put our horizontal asymptotes and our vertical asymptotes on. So I'll try and use this. So our horizontal asymptotes occur at f of x equals 3. So up here, oh my goodness, that's huge. I'm going to have to make that smaller. Let's see if I can. Okay, so maybe that's okay. So there's our horizontal asymptote. Our vertical asymptote is at x equals 2. I wonder if I can just clone this. And then, so we'll put this over at x equals 2. All right. This is okay. Okay, so we've got our asymptotes in. Good. We should plot any points that we figured out. So I can see that I've got a point, that's my x-intercept, right, at 1/3. So this is the point 1/3, 0. This is the point 0, 1/2. So I should plot those. So 0, 1/2 would be ish here. And 1/3, 0 is over here. This is 1, so 1/3. Okay. As you can see, I've got 2 points within one of my branches because I'm going to have a branch like this approaching these asymptotes going through these 2 points. I don't have any points in this upper branch here. So I can go ahead and just based on what I know so far, let's see if we can verify with our positive intervals. From negative infinity to 1/3, so this is my 1/3, my graph was positive. Yeah, that's true, right? This is what I'm going to approach. Then it's going to be negative from 1/3 to 2, not including 2, because we're going to be at our asymptote. That looks like it's curving back, but hopefully you understand that that's not the case. So let's draw that a little better. There we go, that's better. We've got a couple of points there that seem to have gotten lost, but anyway, there's 2 points. I'm going to label one of them. How about the point 0, 1/2? And over here, I don't have a point, so I'm going to pick a point. Let me just look at my equation. I'm going to pick 4 So I'm going to find f of 4. So f of 4 is going to equal 3 times 4 minus 1 over 4 minus 2. So that's going to be 11 over 2. F of 4 equals 11 over 2. Well, that's 5.5, right? So when x is 4, I'm at 5, and 5.5 is there. There's a point on my branch, and now I can draw that branch. And you are going to double check here. From 2 to infinity, our graph was above the x-axis. According to this, it was positive. Okay, I don't know why my branches are 2 different colors. They really shouldn't be. Let's put some, it's all part of the same graph, right? These are both pieces of that graph. Oopsie, shouldn't be touching that asymptote. And I will just label that then 4 and 11 halves. So I had to go and actually find another point because the 2 points that I did have both fell in one branch. But say one of the x-intercepts was over here and one of the y-intercept was on the other branch, that would have been fine. Then you would have had one of each and you wouldn't have needed to do anything else. You're going to label the equation. So f of x equals 3x minus 1 over x minus 2. This is x equals 2 and y equals 3. Okay, and we've got our equation. All right, let's keep her going. All right, determine a possible equation of a function in the form f of x equals ax plus b over cx plus d that has the following characteristics. Now, there isn't any one great way to solve this. You really just have to think about this. I will give you sort of my technique for coming up with these equations. So we're being told that the horizontal asymptote occurs at y equals a half. So you know the horizontal asymptote is a half, and the horizontal asymptote was the coefficient of the x's, as you recall. So a over c equals 1/2. The vertical asymptote, well, that's at x equals 4, and the vertical asymptote was that minus d over c. So we have that minus d over c is equal to 4. So yeah, and then the y-intercept occurred. The y-intercept is where x equals 0, so that was our b over d. So the y-intercept would be b over d equals -4. So start with the horizontal asymptote. So we're starting with this equation, f of x equals ax plus b over cx plus d. So we know that a over c has to equal 1/2, or it can really be any multiple, right, that reduces down to a half, like 2 over 4 or 4 over 8. So let's just start with the reduced fraction of 1 over 2. So we'll put that in. So we've got f of x equals 1 times x plus b over 2x plus d. So far I've got that the coefficients of my x's is a half. So far, whoopsie, so good. We can just erase this. Now we've got to put in either the vertical asymptote or the y-intercept. So we can start with the vertical asymptote. This has to be equal to 4, which means that this, if I have 2x plus something, I'm going to take 2x plus d. That has to equal 0, vertical asymptote. The x is going to equal 4. So 2x plus d has to equal, let's see, it has to equal, something's happening, has to equal 0. So 2x equals negative d and x equals negative d over 2. So in order for that to equal 4, then negative d equals 8 and d equals negative 8. So we would go over here and we would add that in. F of x equals x plus b over 2x minus 8. So when x equals 4 here, you're going to get 0. Okay? All right. That's one way that you could have looked at it. You could have also, this is your c, right? Your 2, so you could have put the 2 in there and then just cross multiply to solve for d. Okay. So far I have a lot of information. I need one more thing to hold true, and that is my y-intercept has to be negative 4, and that comes from my b over d. So over here, we would say that b over d, which is negative 8, has to equal negative 4. So when I cross multiply to solve for b is equal to 32. So let's put that in. X plus 30, did I say negative 32? I think I'm getting tired. 2x minus 8. Let's double check. Coefficients, that gives us our horizontal asymptote. That's 1/2. If I put an x of 4 in, I get 0. So my vertical asymptote is 4. Over here, if I put in 0 for my x's, I get negative 4. And that is all of those characteristics. Okay? So you kind of just have to play around with it, substitute some numbers in here and there, but always just start by subbing one of them in as is and then working with the rest. You might have to work with multiples of numbers to kind of get everything to work out nicely. Okay, that's the end of the lesson. We didn't discuss the whole situation, and I'm going to have to go back and see if maybe that comes up in the next lesson. And I'm pretty sure that it does actually come up in the last lesson. So don't worry that you're sort of still perplexed about the whole idea of a hole in a graph. We will discuss it in a later lesson. All right, thanks for listening. Good night.